workflow, I will show you how you can train a gradient boosting framework in order to classify cloud types. The workflow makes use of Cumulo, and Cumulo is a benchmark data set that provides hyperspectral satellite images at a global scale and cloud labels for a subset of pixels along the track of the satellite. The workflow introduces you to a gradient boosting framework which uses ensembles of tree-based learning algorithms. And this approach is a computationally a very efficient approach and provides models also with high accuracy. And with this, I suggest that we jump right into the notebook. Okay, so we are in week 6, which shows you climate applications. And so we are here on our learning or training platform. We are in week 6, and the respective workflow is the workflow with the number 6C, which is called Cumulo Cloud Classification. And so here there's one notebook, and you see a set of different folders related to data and also some additional helper functions. This workflow shows you how to train a gradient boosting of decision trees for classifying clouds. And the aim is to classify clouds based on one of the 8 cloud genera defined by the World Meteorological Organization. The workflow makes use of LightGBM, which is a gradient boosting framework that uses ensembles of tree-based learning algorithms. And this is usually an approach that is known to be computationally very efficient, and at the same time the models provide a high accuracy. The workflow makes use of Cumulo, a benchmark dataset for training and evaluating global cloud classification models. And Cumulo merges 2 satellite products from NASA's A-Train constellation. One product is the Moderate Resolution Imaging Spectroradiometer, also known as MODIS data on board the Aqua satellite. And the other product is the 2B CLD class LIDAR product, derived from the combination of CloudSat cloud profiling radar and Calypso cloud aerosol LIDAR data. We provided you some more information on the specific data sets, but I think here the visual representation is very helpful to better understand the Cumulo dataset itself. So on the left you see a visible band, and on the right you see the respective cloud mask, and on both of the images there is an overlying label mask that shows the cloud type or the cloud class of colored pixels in one specific vertical track. So Cumulo, the benchmark dataset, brings these complementary data sets together. It contains over 300,000 annotated multispectral images at a 1 kilometer times 1 kilometer resolution, providing daily full coverage of the Earth for 2008, 2009 and 2016. Cumulo data is available in NetCDF and provides cloud labels for 8 different cloud types. And these cloud types are shown here. So it ranges from cirrus clouds to altostratus, altocumulus, stratus, stratocumulus, cumulus, nimbostratus, and deep convection clouds. And then here as well, we start, as we always start, by loading a set of libraries at the beginning. And so here we load some libraries from scikit-learn, but also common libraries from matplotlib and pandas, and also some additional Python scripts that this workflow is using. And these Python scripts you can find in the source folder, which is also part of this workflow's full overall folder. And then here we also define a helper function that helps us to read netcdf files. So the first step in this workflow is to load the Cumulo benchmark data and also to prepare the data for the machine learning model. So this workflow makes already a subset of the Cumulo benchmark data available, and this is available in the data folder. But in case you also want to reproduce the example on your local machine, we also provided you the command which you can use in order to download this specific subset of the Cumulo benchmark dataset. And the subset of the Cumulo benchmark dataset consists of 150 files in the netcdf format. And if you have a look to the data folder, you see here two folders, and in the folder netcdf you see 150 files, and the naming terminology is as follows. So it starts with A, then it's followed by Y, which is identifier for the year, then D for day, then dot, and then we also have information on hour and minutes per day. And so if we see here, we have here files from 2008, the 18th day of the respective year, and then in every 5 minutes we have cloud label information. And so the data files we provided you here are valid for the 18th of January 2008. And in order to get a better feeling of what the data also offers and contains, we open one file and inspect its content. And we can open netcdf files with the dataset constructor of the netcdf library. And if we open this, so this is what we do here. So we create a dataset object with the netcdf library. And we see that each file contains quite a few variables. So in total, we have 31 variables related to longitude, latitude information, but also cloud effective radius, cloud phase optical properties, cloud mask, cloud layer type, etc. And so Cumulo provides different types of features which are called channels per georeferenced grid point. And we make use of the following information. So we use the 13 calibrated radiances which are available, and these radiances we use as input channels because they capture the physical properties needed for cloud classification. Then we use the cloud labels as ground truth data and one label per tile. Then the cloud mask itself to select which grid points we also want to analyze. So because we're only interested in the cloud information, so in the cloudy pixels, and the cloud properties for physically validating our model. And these channels are derived from the raw radiances and provide higher level properties of a cloud, such as top pressure, temperature, etc. And so here is the list of variables we are interested in. So we load the coordinates for each of the cloud pixels, latitude and longitude, then the radiances, which are 13 calibrated radiance information, properties, which include cloud effective radius, cloud phase optical properties, cloud optical thickness, etc. Then the cloud mask, and of course the labels, which have the variable name cloud layer type. So the next step is to extract from each file tiles with a 3x3 pixel window size. And these tiles will be used as input to the machine learning model. And the 3x3 pixel tiles are sampled around each labeled pixel of an image. And this is here just to prepare these operations. So we indicate the path of the netcdf files. We indicate the output path. We also say if the folder doesn't exist, then please create this directory. And then we retrieve all the netcdf files available in the data folder. And the next step is optional because we also provide you already the processed NPSat files, which is the result of this operation. And so in principle, we just want to show you how the NetCDF files are pre-processed and prepared in order to prepare it for the machine learning model. And so what this code is doing, we first extract the required variables from the NetCDF file with the helper function read_NC. And the function loads a NetCDF file and returns 4 masked arrays with the required radiances, properties, cloud mask, and cloud labels. Then we apply the function extract cloudy label tiles, which extracts all the tiles from a cloud area that are labeled. And then the last step is that we save the tile-based radiances, properties, cloud mask, cloud labels, and location information as a NPSat file. And for each day, the NPSat file is stored also under the data folder, but in the NPSat folder within the data folder. And so you can go to the data folder here, and you see here that in the NPSat folder, we already pre-processed this step for you. So the next step is then to load the pre-processed data in the NPSat format, which we then use for training the machine learning algorithm. And we can do this by using the Cumulo dataset, which is also a helper function provided by the workflow. And this is a constructor which loads the tiles which we have just extracted. And when it is called, it returns the radiance channels that we want to use as input and the labels that we use as output in order to train the gradient boosting framework. And as a tile can have multiple labels, the Cumulo dataset returns only the most frequent ones. So the Cumulo dataset constructor requires the directory where the NPSat files are stored and also the extension format of the files, which in this case is NPSat. And so once we created the datasets, we want to load all the tiles at once and also vectorize them because this is the required format by the light GBM model. And the result are the following vectorized tiles, and this is what's happening in this part. So we have the radiances as input variable to the model stored as x. And then we have the y variable, which is the output variable for the model, which are the respective cloud labels retrieved from the Cumulo dataset. And then we have also a variable called p, which offers the physical properties which are used later to evaluate the outcomes on a physical level. And this is what we do here. So we retrieve the respective information and prepare them into a format that can be read by the light GBM model. So if we have a look to the dimensions of the input, output, and properties arrays, we see that in total 63,945 tiles were loaded, and our input variables contains 117 variables or parameters. Our output array only contains like the labels itself, so only one label per tile. And then also the physical properties contains for each tile also additionally 81 parameters that are used to evaluate the physical properties. And so now we are in a state that we can split the input and output variables into 3 different subsets for training, validation, and testing. And so the training data is the actual sample used to train the machine learning model. The validation data is used to evaluate the model during training. So after each training cycle or after each epoch, the model is validated against this validation data. And so the validation data is used for validation, but the model is not trained or does not learn from this specific data. And then the test data is used to provide an evaluation of the final model, and it is only used when the model is completely trained. And so it is important to define these three different subsets, because this allows us for a proper and correct evaluation of the model performance, and also to ensure that a model is not just simply memorizing its training data. And so the way how you can create these three different subsets is a very common approach is to use the function called train_test_split from the scikit-learn package, which splits the arrays into two different subsets. And the function itself takes the following keyword arguments. So it takes the input and output data arrays. It takes the test size, which is a float number representing the proportion of the data set that should be used for testing, and the random state, which is an integer and helps us to assure a specific reproducibility of the random shuffling of the data. So this is what we do here. So we apply the function twice. So first we split the input and output variables and use 20% for testing and 80% for training. And then the next step is we use the training data, so the 80% of the overall input and output data, and there we use 10% for validation and 90% for training. And so if we then also print the dimensions of the three subsets, we see the respective percentages of the overall input and output information. So now we loaded the Cumulo benchmark data set, we brought them into a shape that can be used for the LightGBM model. We also split the data set into three different subsets for training, for validation, and for testing. And the next step is now to define the LightGBM model and also to train it. And so the next step is then to load the LightGBM library and to convert the training and validation subsets into a LightGBM basic data set. And we can do this with the dataset constructor from the LightGBM library. And the constructor requires input and output subsets for the model. And so this is what we do. We create a data set for training. So we apply the dataset constructor from the LightGBM model, and we provide the constructor our training dataset input and output. And the same we also do for the validation. And so we here provide the validation input and validation output subset. And so the next step is to specify a set of hyperparameters, and hyperparameters can be used to fine-tune a machine learning model. And LightGBM offers several algorithms, and the hyperparameters strongly affect the performance of a model. And so here we propose a specific set of hyperparameters and also the specific settings. So we also invite you to really have a look to the hyperparameters in different settings and also playing around to get a feeling of how the output changes if you change a specific hyperparameter here. So the hyperparameters we specify are a boosting type, objective, number of classes. So in our case, because we want to predict one of 8 cloud types, the number of classes is 8. The number of iterations is basically a training cycle. So the number of iterations where at each iteration a new decision tree per class is fit onto the data. Then the number of leaves, which we set here to 31. The learning rate, and we also set verbose to 0. So this is the verbosity level, which only prints errors and warnings. And once we defined the set of hyperparameters, the next step is then to run the algorithm on the training data subset based on the hyperparameters we just defined above. And we can use the function train from the LightGBM library, and the function takes the following keyword arguments. It takes params, so the defined hyperparameters which we defined here, then the data set, so this is our training data subset, and also the validation data subset. And then we can train it, and because we defined 400 iterations, the model is trained, or the model has 400 training cycles. And we see here, so it has been pre-trained already just for training purposes, but we see that at around 380, or at cycle number 382, we see that the model starts to overfit. So now we trained the LightGBM model, so the gradient boosting of decision trees. And the next step is now to, with the help of the pre-trained model, to predict cloud classes with the trained LightGBM model. And above we can see that at iteration 380, the model overfits. And this means that a model starts to memorize the training set and its performance on unseen data. So for example, the validation data set decreases. And so in the end, we are interested in the model with the highest performance to make cloud class predictions. And the model is the one where the validation loss is lowest. And so the best model from the training process can be identified with the function gbm.best_iteration. As a next step, we want to use the best model to make predictions on the training, validation, and test data subsets. And at a later stage, we can then evaluate the model's performance to predict the respective data sets. And so we can use the function gbm.predict, which allows us to predict cloud types based on the trained LightGBM model and the training, validation, and test input data respectively. And this is what we do here. So with the pre-trained model, we predict on the 3 different data subsets on training, validation, and testing. And the output of the prediction process is for each of the input tiles a vector indicating the probability of each of the 8 cloud classes. And this is why we also have here on the columns 8 column information. So for each of the 8 cloud types, we have a probability of this specific cloud class. And the final predicted cloud class is then the cloud type or the class with the highest probability. And this is what we do here. We select the maximum argument of the 8 columns of the NumPy array with the function argument max. And this is what we do here. So from the 3 predictions of the 3 subsets, we select for each of the input tile the maximum probability, which is the final predicted cloud class. And if we then check the dimensions of the 3 subsets, you see then that we only have one predicted cloud information for each of the 3 subsets. So after predicting the cloud classes with the help of the pre-trained LightGBM model, we are now interested how the model is able to predict. So we are interested in how is the performance of the model. And so the next step is then to evaluate the model performance. So an important step after the prediction process is, of course, to evaluate the predicted cloud classes. And we will, in the next section, we will show you different options, how you can evaluate a performance of machine learning models and specifically also classifications. And we start with creating and analyzing the confusion matrices for the predictions. And the confusion matrix is a common table layout that allows the visualization of the performance of a classification algorithm. And we can compute a confusion matrix with the function confusion_matrix from the scikit-learn package. And the function takes the following arguments. So we give it as an input the vector of ground truth classes, which is our ground truth labels, which we loaded from the Cumulo benchmark dataset. Then a vector of the same size of the predicted classes. So these are the predicted cloud labels which we just predicted based on the light GBM model. Then we provide the function labels, so the classes for which the scores are computed. And at the end, we can set normalize to true in order to return ratios instead of total counts. And this is what we do here. We apply the function confusion_matrix to the 3 subsets. And the next step is then to visualize the 3 confusion matrices as a heat map. And you can use the function heat map from the Seaborn library to visualize a confusion matrix. And this is what we do here. So for the 3 training subsets, so this is for the training subset, this is for the validation subset, and this is for the test subset. And the confusion matrices above show you that the light GBM model was able to almost perfectly fit the training data. So in all the classes we have very high performance, but however on the validation and test data subsets the predictability of the model is lower. And in particular the model shows good performance for the cirrus class, for class 0, but for example for tiles of class 7, deep convection, they are often misclassified as either cirrus or ultrastratus clouds. So additional metrics that can be used in order to also evaluate the overall performance of the model, we can use 2 metrics that are also quite common for assessing the general quality of a machine learning classifier. And one of the metrics is accuracy, which is the general rate of correctly classified tiles. And the other one is the average F1 score. And F1 score is a metric that accounts for the model precision and also recall. And recall is the ratio of true positives over all tiles of that class. And it gives us a metric for each of the cloud type. The good thing is also that the scikit-learn library also offers functions for those 2 metrics. So we can use the function accuracy score and F1 score to calculate these 2 metrics. And F1 score can range from 0 to 1, with 1 indicating a perfect precision and recall. And this means like the higher the F1 score, the better. And accuracy the same. So if we have an accuracy of 1, the model is fit perfectly. And so we see below that the model performance has an accuracy score of around 0.84. So this indicates that the model is 84% accurate, and we have a slightly lower F1 score. So now we reach the end of the notebook, and yes, please feel free to also explore the notebook, to play around with hyperparameters and to practically also understand better the light GBM, so gradient boosting of decision trees, and also the Cumulo benchmark dataset.